Hi, my name is Pedro Silva. I'm a postdoc researcher at the HPI, and I will present our solution for the current challenge, which is called Incremental String Query Analytics. Before thinking about designing our solution, we first profiled the current challenge baseline in order to identify some improvement opportunities. We call that baseline GCB Python in this presentation. Here to the right, we have a table with the values of the execution time, latency, and accuracy for the execution of the baseline on scenarios 1 and 2 with datasets 1 and 2 respectively. Below, we illustrate the distribution of the execution time among the different steps of the baseline execution. First thing to notice here is the long execution time and even detection time of the baseline. After analyzing it, we noticed that Python and the clustering algorithm DBScan were mainly causing that. We can also notice high parsing times, in particular in scenario 2, that was caused mainly by an inefficient parsing lib and the sorting algorithm used to identify late or missing records. Finally, we observe a low accuracy in scenario 2. This is caused by the fact that the baseline basically ignores late or missing records. Aiming at those improvement opportunities, we came up with Simbad, the sequential incremental DBScan-based event detection algorithm. It is 26% more accurate than the baseline, but has execution times up to 38 times smaller and latencies up to 7 times smaller than the baseline. We achieved that through 4 dimensions of optimization: programming language, parsing library, clustering algorithm, and the handling of late and missing records. I'll go through those dimensions in the next slides. We start with dimensions programming language and parsing. In Simbad, we re-implemented the detection algorithm in C++. We replaced the parsing library by rep.json, and we also replaced the algorithm used for sorting records and identifying late and missing records by an efficient O of N algorithm. Those optimizations plus the reimplementation of DBScan in C++ compose the baseline GCB C++. As it is 36 times faster than GCB Python and has up to 7 times lower latencies, as you can observe in the table below, from now on, in this presentation, we only use GCB C++ as a baseline. The next dimension of optimization is the clustering algorithm, which for the baseline is the DBScan. In Simbad, we replace DBScan by the incremental DBScan, a clustering algorithm based on DBScan that fits perfectly the incremental characteristic of the feature window. Furthermore, it has a complexity of O of N instead of O of N squared. The incremental DBScan is taken from the literature and is described on the reference below from VLDB 98. Now let's talk about the last dimension of optimization, which is the handling of late and missing records. When we talk about late and missing records, we talk about incomplete features, which are features calculated with less than 1,000 records. Using incomplete features for calculating solutions for the event detection can lead to accuracy issues. That happens because the value of an incomplete feature might be very different from the value of a complete feature. In the example below, we have the representation of the feature space with active and reactive powers, a few features represented by black circles, and an incomplete feature I. The value of I may be different from the value of the complete version of I. For example, after the arrival of the late records, I could actually be inside of that cluster or outside of it, or create a new cluster with another feature. So to improve accuracy, it is important to wait for late records to arrive before calculating the value of features. That's the job of the noise buffering mechanism, which allows Simbad to wait for late records to arrive before processing them. However, it's important to highlight that there is a trade-off between accuracy and latency. The more we wait for late records, the largest the latency will be, but also the most accurate the solutions will be. Having that in mind, in Simbad, we consider a feature to be incomplete only if it is calculated with less than 900 records. We arrived to that threshold empirically after analyzing the two available data sets that we had. In this slide, we have some metrics from the current version of Simbad, which includes the incremental DB scan, noise buffering, and the programming and parsing optimizations. We can see that in comparison to the baseline, there is an improvement of the execution time of around 4.5% and an improvement of the accuracy of around 26%. At the same time, there is a degradation of the latency of around 6 times, which is the result of Simbad waiting for late records to arrive before moving with the execution. This makes clear that trade-off between latency and accuracy that I mentioned in the previous slide. And with that in mind, we came up with another mechanism to deal with late and missing records, the quick result calculation, the QRC, which in summary searches for features in the feature window which are not part of events independently of potential incomplete features. The design of QRC is based on two constraints used by the event detection algorithm. The first constraint is that a feature can't be part of an event if it belongs to a cluster. In the example below, we illustrate the situation. We have in the feature space of active and reactive power one incomplete feature I, a few features inside of a cluster and a noise feature F. All features inside of the cluster will be part of the cluster independently of the value of the complete version of I. So those features can never be part of an event. Feature F, however, depends on the value of I, since I can be close enough to F to form a cluster. The second constraint that we use states that an event can't be inside of the temporal interval of a cluster. In the example below, we have the timestamp of the features in the x-axis and the reactive power dimension in the y-axis. In order not to have a 3D graph, I don't use the active power axis, but the idea is the same. Here, the time interval of the yellow cluster is defined by features A and B. Any feature inside of that time interval can't be part of an event. Hence, I and F can never be part of an event. Finally, QRC allows the execution not to block completely. While noise buffering is buffering incomplete features, QRC sends results to features which are surely not an event. Here we can observe the performance of Simbad with QRC. In the table below, we can notice that QRC managed to reduce the latency resulting from waiting late records by around 2.5 times. Now it is around 2 times worse than the latency of GCB C++. At the same time, Simbad maintains an accuracy of 26% better than GCB C++. The grand challenge only considers true positives for the calculation of the accuracy. However, Simbad also improved the detection of true negatives. In the table below, we can notice that the F1 score is 48% better, the precision is 26% better, and the recall is 69% better. The profiling of Simbad shows how we managed to reduce the share of event detection in the execution time, which is now it's around 0.5%. It also shows that download and upload times are responsible for 88% of Simbad execution time. That happens mainly because those steps are completely sequential. The next steps will be naturally to reduce those times by adapting the event detection algorithm to a parallel execution. It's important to mention, however, that the current version of the evaluation server will process a maximum of only 2 parallel requests. Well, in this presentation, we introduced Simbad, an event detection system capable of calculating solutions up to 26% more accurate than the baseline, and with an execution time up to 38 times smaller, and latencies up to 7 times smaller. For that, we used off-the-shelf tools such as C++, RapidJSON, and the Incremental DB scan. And in particular, for scenario 2, we came up with 2 optimizations for handling missing and late records. the noise buffering, which allows SimBot to buffer missing data, and the quick result calculation, which discard features without having to wait for late data. So that's it. Thank you a lot. And now it will be my pleasure to answer any questions.